We're in section 5.4.2, converting to and from polar coordinates. So based on the diagram below, which is the diagram of a right triangle associated to a point P, we can see relationships between x, y, r, and theta, which are the relationships of a right triangle. So in particular, we have the trig relationships that the adjacent over the hypotenuse is the cosine, and so x is r times the cosine of theta. Similarly, we've got the opposite over the hypotenuse, which is the sine, and so y is r sine theta. Continuing with the trig relationships, we have the opposite over the adjacent, so the tangent of theta is y over x. And lastly, we have the Pythagorean relationship that x squared plus y squared is equal to r squared, so r squared is x squared plus y squared. In example 5.4.3, we're going to convert points from rectangular to polar coordinates and vice versa. And then on the next page, we'll convert equations from polar to rectangular and from rectangular to polar. So starting with example 5.4.3, we'll start with the first of the points, 2 minus 2, which we're asked to convert from rectangular to polar coordinates. So let's plot that point first. So 2 over in the x, minus 2 down in the y. There's our point 2 and minus 2. We need the radius first. So r, which is going to be that distance there. So r squared is x squared plus y squared. So 2 squared plus minus 2 squared is 4 plus 4 is 8. So r is the square root of 8, which is 2 root 2. We also need the angle theta, and we can see in the diagram that it's an angle of 45 degrees, or minus pi over 4. But let's use the relationships. We know that the cosine of theta is x over r, which is 2 over 2 root 2, or 1 over root 2, which is root 2 over 2. The sine of theta is y over r, which is minus 2 over 2 root 2, or minus root 2 over 2. And so we're looking for an angle theta on the unit circle that has those coordinates, and we know exactly where it is. In fact, it's equivalent to this one. We know indeed that that angle theta is minus pi over 4. And so our point 2, minus 2 in rectangular coordinates can be described in polar coordinates as 2 root 2 and minus pi over 4. Remember that in polar coordinates, the description is not unique. We could go around that unit circle in either direction multiple times and get a different angle. We could also, for that matter, give a negative radius and add pi to the angle, as we saw in a previous video. All right, so that's the point 2 minus 2. Let's look now at the point that's given in polar coordinates and convert it to rectangular coordinates. So let's start the same way. Let's plot that. So if we plot our point, so we know how to plot polar coordinates. First of all, we draw axes that are not crooked. We need to go at a distance of 1 unit, and we need to go round an angle of 3 pi over 2. So 3 pi over 2 is going to put us, well, that's 1 pi over 2 and 2 pi over 2 and 3 pi over 2. So there is our point, 1 pi over 2, and this is our angle going around here of 3 pi over 2 and our distance of 1. So there's our point in polar coordinates of 1 and 3 pi over 2. Now converting this direction is actually much easier. We're going to just plug in into r cos theta and r sine theta. So x is r, which is 1, times cos of 3 pi over 2, and the cosine of 3 pi over 2 is 0, and so 1 times 0 is 0. Y is r sine theta, and so now we have 1 times the sine of 3 pi over 2. The sine of 3 pi over 2 is minus 1, so 1 times minus 1 is minus 1. And so that point here, 3 pi over 2 in rectangular coordinates, is the point 0 in x minus 1 in y. All right, example 5.4.4, we're asked to convert the following equations into polar coordinates. X squared plus y squared is equal to 9. We know that that is a circle. Well, using our relationships from up above, x squared plus y squared is r squared. So r squared is equal to 9, or quite simply, r is equal to 3. So that is a very nice, simple, easy way of describing a circle centered at the origin. Right? So you can see an advantage right away, simplicity of some curves in polar coordinates. Part B, so y is equal to x squared. Well, we're going to fill in that we know y is r sine theta, and x is r cos theta, so we're going to get r squared cos squared theta. And we saw in a previous video that very often for polar coordinates we have r is f of theta. Did we see that, or are we going to see that? It's so many videos, folks, so many videos, I don't know anymore. Regardless, r is f of theta is the usual form for a function in polar coordinates, so we want to isolate r. Now, we have an r on both sides, and as long as r is not equal to 0, if r is not equal to 0, then I can divide by it, and I'm going to get sine theta is r squared cos, no, r cos theta. R cos squared theta, one of these days I'll get these, right? And so if I want to isolate r, I'm going to divide. So I'm going to get sine of theta divided by cos squared theta, which can be written as sine over cos tan theta times 1 over cos, which is secant theta. So there is everybody's favorite parabola, y is equal to x squared, rewritten in polar coordinates. Lastly then, example 5.4.5. Now we're going to convert equations, they're given in polar, and we're going to convert them to rectangular. So r here is cos theta plus 2 sine theta. So we want to make our lives a little bit easier. There's nothing that says we can't manipulate the equation a little bit first before we convert. We have the relationships above that involve r squared as x squared plus y squared. So I'm going to multiply both sides by r, which is actually kind of nice on the right-hand side as well, because then we get the relationships r cos theta and r sine theta, which we should remember from up above. So r squared is x squared plus y squared. R cos theta is x plus 2r sine theta is y. So there's our equation converted, and that, if we bring it over, right, you might see that you could do x squared minus x plus y squared minus 2y is equal to 0. If you complete the square, you should see that that actually turns out to be a circle as well. Well, why don't we just do it? Why don't we just do it, folks? Why don't we do it? X squared minus x, if we divide by 2 and square, we get plus 1/4 plus y squared minus 2y, divide by 2 square, which is 1, so I have to add 1/4 and 1 on this side, so let's clean that up. That is going to be x minus 1/2 squared plus y minus 1 squared is 4 over 4, 5 over 4. And so there we have a circle centered at 1/2, 1, and the radius of root 5 over 2. So I got carried away a little bit. This would have been fine as a final answer to convert there, but there now we actually see what the graph looks like. And the last one, here of example 5.4.5, we're asked to convert r is 3 secant theta into rectangular coordinates. So let's rewrite the secant as 1 over the cosine, multiply up, and we have r times cos of theta is equal to 3. Well, that's super convenient as well. That is x is equal to 3, and so that is actually the equation of just a vertical line. The vertical line where x is equal to 3 is in polar coordinates, r is equal to 3 secant theta. So there we go, converting to and from polar coordinates. In the next video, we'll take a look at some graphs in polar coordinates, things that are called polar curves.